So welcome to the video solution of day 24 Wednesday questions. So in this video solution, I'm here to solve a very important question that is for gate. And the question is a filter connected to a rectifier, and this is a circuit. Okay. So we will be analyzing the circuit for the diode current ID. We will be solving for ID peak value and ID average value. Okay, and both of these are very important. Okay, gate has asked a question on ID average value in the previous year gate questions of electronics, and we will be focusing on ID peak also, and we'll be solving for ID average also. Okay, and the reference that I'm taking is Microelectronics by Cedra Smith Pope. Okay, so first of all, let's solve the circuit. So this is a diode. So first of all, let us solve the ideal case. This is a capacitor, this is the input Vi. Okay, and there is no resistance connected across the capacitor. This is the output voltage. Okay, now this is P terminal of the diode, this is N terminal of the diode. So let us initially assume that capacitor is initially uncharged. Okay, it is initially uncharged. So since it is initially uncharged, and we will see that the voltage at this N terminal will be 0, and we are assuming that Vi is positive. So I'm just taking this as the input. Okay, so this is as the input, this is Vi. So we can say that since Vi is positive initially and capacitor is initially uncharged, so N terminal is at 0 volts and P terminal is connected to Vi. So since Vi is positive, so Vi will push this battery, Vi will push current in this direction. Okay, and the diode will turn itself on. Okay, when the diode will turn itself on, so P terminal will get connected to the N terminal, and we can see that this Vi is directly short circuited to the capacitor. Okay, and since there is no resistance in the path, so the RC time constant will be 0, and the output voltage will start following the input voltage, and capacitor will start getting charged with input voltage Vi. Okay, so if I draw the output Vo, so it will start following the input till here. Now at this time instant, we can see that since this is T1, let us say, so we can see that at time t equals to T1, the voltage across capacitor is, let us say this is V1 volts, so capacitor is charged with V1 volts. This is the diode and this is input voltage Vi. Okay, now here we can see that at t equals to T1 plus, that is just ahead of T1, this input is getting below V1 volts. Okay, so input is getting below V1 volts. This is P terminal, this is N terminal. So N terminal is having high voltage than P terminal, so diode will turn itself off, and when the diode is off, the capacitor will get an open circuit both sides. So when the diode is off, the circuit will become like this. This is Vi, Pn, and the capacitor C. So capacitor is charged with voltage V1, and since Vi is less than V1, so diode will turn itself off, and thus the output voltage remains at V1 only. Now at time instant T2, when Vi tries to go above V1, okay, here we can see that at this point, at this time instant, Vi is getting above V1. So when Vi is getting above V1 volts, so again diode will turn itself on, and diode will get short circuited, and output voltage will be followed by the input voltage, and capacitor will get charged, and at this time instant, let us say this is T3, the output voltage is V3. Okay, now again here we can see that input is getting below V3, and V3 is the voltage across the capacitor at time instant T3. So diode will turn itself off and output voltage will remain constant till this point, that is T4. At time instant T4, input is getting above V3, so output will follow the input, diode will turn itself on, and again it will be like this, and then it is like this. Okay, so we can say that when diode is on, then output is equals to input, and capacitor is getting charged with Vi volts. Okay, and when the diode is off, then output is equals to the voltage across capacitor, and when the diode is off, then the circuit is like this. Okay, and here we can see that the capacitor does not have any connections around itself, so, and capacitor has no connections, so current through the capacitor is equals to 0, and voltage across capacitance remain constant. It does not change. Remain constant. It does not change with time, as we can see here. So here the capacitance across voltage across capacitance is constant. Here also it is constant. Here it is constant, and here it is constant. Okay. So if you have seen the previous videos on the diode circuits, I have explained this. Okay. In case of capacitance also, in case of communications also, when I have explained the envelope detector, I have explained this circuit there also. So this is the ideal case. Okay, so suppose the ideal case, let us say the ideal case, and the input is a sinusoidal input. Okay, so if the input is sinusoidal, okay, so it is like this. So this is input volts. So we can say that initially we assume that the voltage across capacitance is 0. Capacitance is initially uncharged. Okay, so when input is greater than 0, diode will turn itself on, capacitance will start getting charged, and at this time instant the voltage across capacitance will be Vm. So diode is on in this time duration, but after this we can see that when input is going below Vm, the diode will turn itself off and the capacitance voltage will remain constant to Vm forever. Okay, so if this is the circuit and input is sinusoidal, green one is the output volts, that is across the capacitance. So this is the output volts. Okay, but if we take the practical case, as we have seen in the question, the practical case is the capacitance connected with a resistance R, input volts Vi. Now if I draw the input Vi, with time t. Okay, so let us say input is a sinusoidal wave. Okay, it's a sinusoidal wave. This is, I'm just taking input as a cos omega mt. Okay, this is time instant 0, this is time instant. Okay, so this is time instant. So let us say the time period is t naught. So this is minus t naught by 4. Okay, and so on. So let us start with the, so let us say that we start with time instant minus t naught by 4 for the analysis. So at time instant minus t naught by 4, the voltage across capacitance is 0. Okay, the voltage across capacitance is 0. So this is p terminal, this is n terminal. So we can say that voltage across capacitance is 0 initially. So n terminal of the diode is at 0 volts and input is going positive. So when the input will go positive, so p terminal will be positive and n terminal is at 0. So diode will turn itself on and the circuit will be like this. This is Vi, diode will turn itself on, this is P, this is N, and capacitor like this. Now since here we can say that the capacitance is directly short circuited with the input volts Vi, so the RC time constant is 0 here, and the voltage across capacitance will follow the input, and this is the output also. So output will follow the input. Okay, it will follow the input. Now at t equals to 0 time instant, we can see that this is capital A. At this time instant, we can see that the input is trying to go below the voltage across capacitance. Okay, the voltage across capacitance at t equals to 0 is capital A. But at t equals to 0 plus, we can say that the input is going less than capital A volts. So diode will turn itself off because the voltage at P terminal is less than voltage at N terminal. And since the diode is off, when the diode is off, the capacitor will be connected to this resistance. Okay, there will be this connection. Now here I have not drawn this resistance because there is of no use, because on this path this capacitance is short circuited because this Vi battery has zero resistance. That's why I have not drawn it here. Okay, it is present but it is of no use. Now when the diode is off, this capacitance will get discharged with this resistance. Okay, so the output voltage will not remain constant as we have seen in the previous ideal case, rather it will go like this. Okay, now at this time instant, again the voltage across capacitance is that is the black one, is less than the input. Okay, the input is the red one, red plot. So at this time instant we can see that the voltage across capacitance is less than the input volts, so the voltage at N terminal is less than the voltage at P terminal, so diode will turn itself on. And when the diode will turn itself on, the output voltage will follow the input till this time instant only. So let us say this is time instant t1. Okay, so till this time instant only. So at this time instant also, we can see that the input is trying to go less than the output or the voltage across capacitance. So diode will turn itself off and the and the capacitance voltage will follow this. It will discharge through the resistance, and again it will get charged to the maximum point, and again it will follow like this. Okay, so this will be the output voltage as I have drawn with the black color. Clear? So now let us see that if we analyze, so first of all let us analyze this with the help of the figure that I have copied from a book. So let us say that this is time instant t1, this is t2. Okay, this is again, so similarly as I have drawn in the previous case, here the voltage is the maximum of the input, the amplitude of the input is Vp. Okay, okay, now this is the output that is drawn with the dark black color. Okay, so it is following as we have seen in the previous discussion. Okay, it is like this, same. Now this is the time period from this time instant to this time instant. This is the time period. Okay, and we are just assuming that the difference between this maximum point of the output volt and this minimum point of the output volt is VR. Okay, we are saying that it is VR. Okay, now first of all let us find out this VR. What is this VR equal to? Okay, let's analyze. So we can say that the output voltage from this time instant t2, so let us say this is time instant t3, this is time instant t4. Okay, so this is time instant t2, this is time instant t1. So from time instant t2 to t3 we can say that the output voltage, that is the capacitance, is discharging through the resistance. So output voltage is has the equation of discharging capacitance, that is Vp e to power minus t by RC from time t2 to t3. Okay, now since this time ranges from t2 to t3, so there will be some modification in this equation, and this equation will be written as Vp, that is maximum voltage, e to power t minus t2 minus sign divided by RC. Okay, why is this so? Because here the time axis is starting from t2 to t3 only. Okay, now at t equals to t2, the V output is equals to Vp. At t equals to t3, V output is equals to Vp e to power minus t3 minus t2 divided by RC. Is it clear? Now here we just make an assumption that t3 and t4 are very close to each other, and the time difference between t2 and t4 is the time period, that is capital T. So we can assume that the time difference between t2 and t3 is also capital T, because t3 and t4 are very close to each other. So VO will be written as Vp e to power minus capital T divided by RC. Now assuming that the RC is very large, let RC is very large, so this exponential will be approximated as 1 minus T by RC. Okay, so this T can be written as 1 upon frequency of the input, so it is Vp 1 minus 1 upon capital T RC is the output volt. Okay, so output voltage at t equals to t3 can be written as Vp minus Vp upon, sorry, it is F upon FRC. Now as here we have seen that I'm just taking the difference between the output volt at this point and this point as VR. So the voltage output at T2 minus voltage output at T3 is equals to VR. So from here we can see that voltage output at T2 is Vp, voltage output at T3 is Vp minus Vp upon FRC. So this is equals to VR. So we can say that VR is equals to Vp upon FRC. A very important relationship. Now let us find out the delta T. Now what is delta T? Delta T is the time difference between T3 and T4. Okay. Now for this we will just do a little analysis. So let us say that the input is Vp cos omega t. Okay. So this is the sine cos curve. Okay, so this is time instant t4, this is time instant t3, this is Vp volts, and here at time instant t3 the voltage, the value of the input, we know that it is equals to Vp minus Vr. Okay, Now let us see that at time instant t3, the input volt and the output volt is same, and at this time instant we know that the output volt is Vp minus Vr. Okay, so let us say that, so we have to find only this time instant delta t, the time difference delta t. So let us say that this is time instant 0 and this is time instance minus delta t. Okay, and since input is Vp cos omega t, so input curve equation is Vp cos omega t. Okay, at t equals to 0, the value is Vp. At t equals to minus delta t, the value is Vp minus Vr. Okay, so we can say that Vp cos omega delta t is equals to Vp minus Vr. So cos omega delta t is equals to Vp minus Vr upon Vp. Okay, now we know that cos omega delta t, or if we write the expression, we know that cos theta is equals to 1 minus 1 upon 2 theta square, plus there will be many terms in this series, but all the higher order terms will be neglected when theta is very small. So here delta t will be very small, so this can be approximated as 1 minus 1 upon 2 omega delta t whole square is equals to 1 minus Vr upon Vp. So from here we can see that omega delta t will be equals to 2 times Vr upon Vp under root. Okay, so this is your value of omega delta t. Okay, now we have to find the value of the average value of the diode current. Okay, now first of all let's move on to the figure. Okay, now as we know that the diode will turn on only in this region. Okay, only in this time instant between t3 and t4 diode will turn on, and then it will turn off, and again it will turn on at this time instant till the maxima of the input, and again it will turn off. So in one time duration, in one time cycle of the input, the diode is turning on only from t3 to t4, that is only for time instant, that is delta t. Now if we see the circuit when the diode is on, then this is P terminal, N terminal, this is the input Vi, capacitance C is connected here, and a resistance load is connected here. Okay, so in this time instant from T3 to T4, the diode is on, so the diode current ID will flow, and if we apply KCL here, we can see that ID will be equals to the capacitance current and the load current. Okay, so ID will be equals to IC plus IL. Okay, IC plus IL. Now first of all let me write that when the diode is on, diode current ID is non-zero, and when the diode is off, diode current ID will be 0. Okay, now when the diode is on, then the diode current is non-zero, and the diode current is equals to the capacitive current and the load current. Okay, now we have to, if we want to find the diode current, we have to find the capacitive current and the load current. Now if we look at from time instant t3 to t4. Now here we can see that from time t3 to t4, the diode is on, so the circuit is like this. Okay, and the diode current is this id, this is ic, and this is il, the load current. Now from time t3 to t4, this is time t3, this is time t4, we can see that the voltage across the load RL, that is VO, is approximately equal to VP. Okay, so we can see that the load current IL is equals to VP upon RL. Okay, and to find out the average value of the capacitor current in this time duration delta t, we will do this. To find IC average, now in time duration T3 to T4, the we know that voltage across capacitor at T3 was Vp minus Vr, and voltage across capacitor at T4 is Vp. Okay, so the charge the charge at T3 in capacitor was C into Vp minus Vr. Charge at T4 in capacitor was C into Vp. Okay, so change in charge is equals to C into Vr, and time duration is delta t. So we can say that the IC average will be delta Q upon delta T, that is CVR upon delta T. Okay, so this is the IC average flowing in the capacitor. Okay, now from this we can say that the diode average current will be equals to the capacitor average current plus the load current. So capacitor average current is equals to CVR upon delta T plus the load current, that is Vp upon RL. Okay, now as we know that omega delta T is equals to under root 2 VR upon Vp. Okay, so we'll put it here. So we'll get that ID average is equals to Vp upon RL plus CVR upon under root 2 VR upon Vp into omega. So this is the equation for ID average. Now this can be further simplified. Now as we know that VR is equals to Vp upon FRC, FRL into C. So we can put this here, and omega is equals to 2 pi F. So we'll get Vp upon RL plus Vp upon RL into 2 pi under root Vp upon 2 VR. So taking Vp upon RL common, we'll get 1 plus pi under root 2 Vp upon VR. Okay, so this is the ID average current. Okay, now to find out the maximum value of the current, diode current in the time duration delta t, we know that ID is equals to IC plus IL. Load current is approximately constant, that is Vp upon RL. So to find out the maximum diode current, ID max will be equals to IC max plus Vp upon RL. Okay. Now let me paste the figure here. Now as we know that the IC current is equal to C times voltage across the, that is dVo over dt plus Vp upon RL. Okay, so we have to find out the maximum value of this current. Okay, in the time duration delta t, that is from T3 to T4. Now as we know that from T3 to T4, Vo is equals to Vi, and we know that Vi is equals to Vp cos omega t. So we can say that ID max is equals to C times D Vp cos omega t divided by dt max plus Vp upon RL in the time duration T3 to T4. So ID max will be equal to minus C omega Vp sin omega t maximum in the time duration T3 to T4 Vp upon RL. Now let us say that this T4 time duration is equals to T4 time instant is equals to 0, and then T3 time instant will be minus delta t. Okay, so from minus delta t to 0 is the time duration. Now at t equals to 0, this will be 0, so it will not be maximum. At minus delta t, this sine term will be a negative term and this term will be maximum. So diode current will be maximum at T3, that is minus delta t. So we can write ID max is equals to minus C omega Vp sine omega delta t plus Vp upon RL. Now we know that when sine theta is approximately equal to theta when theta is very small. So this can be written as plus C omega into omega delta t into Vp plus Vp upon RL. I think I have to add one more page. Okay. Now omega delta t can be written as under root 2 Vr upon Vp plus Vp upon Rn. Now if we multiply, first of all, this can be written as C omega under root of 2 Vr into Vp plus Vp upon Rn. Now multiply by under root Vr by numerator and denominator. So we get C omega Vr under root 2 Vp upon Vr plus Vp upon Rn. Now we can write Vr as 2 pi Fc. Okay, Vr can be written as Vp upon Frc under root 2 Vp upon Vr Okay, so FC will cancel out. This will come out to be 2 pi Vp upon RL. Okay, so we will take Vp upon RL as common. So we get 2 pi under root 2 Vp upon Vr plus 1. So this is the ID max. Okay, so these two equations are very important, ID max and ID average. So we have solved the maximum diode current in the half wave rectifier. Now let us say if we have a full wave rectifier, then what will happen? So full wave rectifier circuit will be something like this. Okay, so this is your load RL, and in parallel to load RL, a capacitor will be connected. Okay, okay, so this is the input voltage and this is the output voltage. Okay, now here we will see that generally without capacitor the output will be like this, full wave rectified circuit in the full wave rectified curve. Okay, without the capacitor the output will be something like this. Okay, but since there is a capacitor, so let us say the capacitor is charged till the maximum value, then it will discharge through the resistance, then it will rise, then it will discharge, and then it will rise, then it will discharge. So let us say that the difference between the maximum and the minimum value of the output voltage is VR. Okay, so in this time duration, that is from this time instant to this time instant, so let us say this is time instant 0, this is time instant t1, this is time instant t2. Okay, so from 0 to t1 we can see that the diodes are off. Okay, and the capacitor is discharging through the resistance. So from 0 to time instant t1, the output voltage will be equals to a discharging capacitor equation, that is Vp e to power minus t by Rc. Okay, it can be approximated as Vp 1 minus t by Rc when Rc is very large. Now if this is Vp, so I'm saying that the minimum value of the output is Vp minus Vr. So at t equals to t1, the output voltage will be equals to Vp 1 minus t1 upon Rc. So let us, since this time delta t, okay, the difference between t1 and t2 is very small, so I can say that the time distance between t1 to t0, t1 to 0 is approximately equals to the time difference between t2 to 0, that is capital T by 2, the time period of the curve divided by 2. So VO is, so I can say that T1 is approximately equals to capital T by 2. So Vp 1 minus capital T divided by 2 Rc. So VO is equals to Vp minus Vp upon 2f Rc. Okay, f is a frequency, that is 1 upon time period. So we can say that the ripple, that is Vr, is equals to Vp upon 2f Rc. Clear? So this is the ripple voltage. Now to find out the delta t, we will do this. Okay, so we have Vr, to find delta t. So we will assume, we know that the output is equal to the sinusoidal curve from the time instant. Let us say this time instant is t3, this is t4. Okay, so VO is equal to VP cos omega t from time instant t3 to t4. Okay, and for simplicity we can say that t4 time instant is 0 and t3 time instant is minus delta t. Okay, so that is from minus delta t to 0. Now to find out delta t, we know that at t equals to minus delta t, VO is equals to VP minus VR. So VP cos omega delta t is equals to VP minus VR, and by similar exercise as we have done earlier, so omega delta t will be equals to 2VR upon VP. Okay, the only change is that here VR is this. Okay, and we can say that in case of the full wave rectifier, VR is less than the VR of the half wave rectifier. Okay, so this is the omega delta t, that is same as that of the previous case. Okay, and similarly we can find ID average also by the same exercise, and we will find that the ID average is also equals to the same equation, Vp upon RL 1 plus pi under root Vp upon 2 VR, doing the same exercise. Okay, and ID max will also be same. The only change in the equation is the change in the value of VR. Okay, so exactly similar exercise to do to find out ID average. Okay, now to find, I'm just giving you a hint here. So ID average will be equals to IC average plus IL. So IC average is, so in the time duration from minus delta t to 0 is the ID average current. So IL is approximately equals to Vp upon RL. IC average is equals to the charge that is supplied divided by the time period delta t. So if the charge supplied is change in the voltage of the capacitance into the capacitance value, that is CVR upon delta t plus Vp upon RL. So exactly same equation is created. Okay, and similarly for ID max, we will write IC max plus IL. Now we know that in the time duration minus delta t to 0, IC max will be C dVc over dt max. So what is voltage across capacitance? So voltage across capacitance is equals to the equation Vp cos omega t from time duration minus delta t to 0. Okay, so we will write ID max is equals to minus C omega Vp sin omega t plus IL. Now this will be maximum at time instant minus delta t, so this will come out to be plus C omega into omega delta t into Vp plus IL. So IL is Vp upon RL. So again we will see that the equation is exactly similar to the previous case. So it will come out to be equal to this equation. So like this, we have solved for ID max and ID average for full wave and the half wave rectifier. Okay, so thank you students.